In this video, we're going to talk about how to program a linear least squares problem or some aspects of the problem in Matlab. To begin with, let's review what we just talked about in terms of linear least squares regression. We start from the premise that we have a model, and in our case, the model will be a linear model. The model parameters are this vector C here, and the system matrix is our matrix B. And we're given some data, which we call this the vector F. And we set up the sum of square differences error function between the model and the data, and we expand, and we end up with a quadratic function, as we just showed. The procedure for solving this, the value of C for which this quadratic function is minimum, is simple. All we have to do is compute the partial derivatives, or compute the gradient of this quadratic function, and set the gradient to 0, and then solve it. And we did this a couple times in a couple different ways, and we ended up with this equation solution. So let's go to Matlab and let's implement this quadratic function and see that this is indeed a quadratic function. The regression problem is indeed a quadratic function. So I have here a simple script that, first of all, we're just going to plot a general quadratic function in Matlab, and just to see how we can program this and how it looks. So here we're going to run the script, and let me clear the workspace. So clear the variables and the workspace. So we're going to run the script, and the first line here, the second line here, will create an array grid of x and y coordinates corresponding to each other. And then I'll just pick some random coefficients for my polynomial, and I will just program the polynomial this way, and then I'll call a figure, and I'll do a surface plot and label the axis. So let's run this, and let's take a look how it looks. So you can see here, first of all, in the workspace, you have several variables now. The x variable here, the x domain, the x coordinates of our domain, it's an array of 21 by 21 coordinates, right? So it goes from -10 to 10. And you can plot, if you want to see the values of x, you can see that it goes a coordinate like this from -10 to 10. The y variables are the same, but now in the y, they vary in the y direction, right? So I take the first element of this y array combined with the first element of the x array, and then I have the coordinate -10, -10. I take this one, and I have -7, -7, right? So we have a set of 2D coordinates here prescribed in this array. We program the z function, which is to be just a polynomial on these coordinates, and then we plot, and here is our plot. And you can see this is a general plot of a two-dimensional quadratic function. Of course, the plot is in 3 dimensions, 4, and so on. It becomes very hard, but in 2 dimensions we can still do it. And the nice thing about Matlab is you can grab or click the mouse and just rotate and see this quadratic function from all sorts of angles. So this is a general script that you can use to program a quadratic function. So let's go back to our problem, summarizing the slide here, right? So let's plot essentially this function when this model here is a line. Right? Let's see, does it really look like a quadratic equation? This is another script that you can use to do this. So first of all, we provide some data, and you create your vector of coordinates. Here I'm just going to plot a particular model, and I'm going to compute the error between the model and the data, and these are the commands that you can use to do that. And here, of course, we're using the transpose of this vector times itself. I think I used the variable z in our previous video, so this becomes d now. So let's run this section and see what we come up with. So here's our data, right? We're plotting the data in these red dots, and here's our model. Now this model was specified here by the slope being 2.5 and the intercept being -1. So you can see it's not a really nice fit, but it's not too bad, but it could be better as a fit, right? So the model here is in blue and the data points are in red. So let's do a surface plot by varying the values of a and b, which again are our model parameters. We're going to vary this a and b from -10 to 10, And for each of these coordinates that we get from this array, we build a different model and compute a different error. And for each of these coordinates and indices of these coordinates in our A array and our B array, let's compute the sum of square difference errors, and let's create a surface plot and see what it looks like. And hopefully, what I said in our previous videos will be true, that this will indeed be a quadratic function. So let's run this section. And here's what you get. So this is the sum of square differences as a function of the parameter A on this axis and the parameter B on this axis. And the z-axis here is how big the error is. So you can see, first of all, if we rotate this thing, this is pretty much a quadratic, right? At least it's easy to see on the A dimension, and in the B dimension it's a little bit more difficult because the variations are much smaller and harder to see by eye, but there is also a slight inclination. So this is a 2D quadratic function, and the mean of this quadratic function is what you're going to use that linearly square solution technique, and this is a color map, so the mean will be roughly somewhere around the darkest point of this plot, which should be right around here, and this will come up in the homework for you to solve. But here is a simple array, Matlab script that you can use to compute these arrays, compute a model, compare it to the data, compute the sum of squared errors, and hopefully this will be enough to get you started to actually solve a linearly squares example like this.